My name is Karan Kara, and I'm a senior.
I'm Alex. I'm Alex Wu, and I'm a senior.
I'm Curtis Ying, and I'm also a senior.
Hello, distinguished judges, coaches, fellow teams, and everyone watching through the live stream. We are Team 17570 from the Blake School in Minneapolis, Minnesota. Today, we will examine the evolution and current scale of housing in two U.S. cities, Albuquerque, New Mexico, and Seattle, Washington. In this presentation, we will use statistical data and predictive models to understand housing instability and homelessness. For our team's global assumption, we concluded that there will not be significant policy shifts concerning housing or homelessness within the next 50 years. Despite the unrealistic nature of such an assumption, we felt as if the policy could introduce uncertainties impossible to predict. Instead, we offer our solution to question 3 as a launching point for solving homelessness.
To ultimately understand the rising homeless issues and propose solutions, our team was first tasked with predicting the number of housing units in these U.S. cities 10 years, 20 years, and 50 years after 2024. Besides our main global assumption, we assumed, based on collected data, that the average number of people living in a home will remain at 2 for Seattle and approach 2.07 for Albuquerque. This is important as our modeling method involves predicting population and dividing by these values to predict the total number of houses. Our method for this question combined 2 different population modeling techniques. First, our team used a simple logistic model, a function predicting population P as a function of time T years after 2010. The main reason for utilizing this model is to determine M sub P, the equilibrium point. As T approaches infinity, P of T returns MP. In this context, it is the maximum population of a given city. As it is unrealistic to assume population grows exponentially or even linearly, any population has a theoretical limit or equilibrium. For Seattle or Albuquerque, this could be due to factors such as expensive housing, stagnation in the job market, or physical limitations of square footage. We derived this maximum number of housing units by dividing M sub P by the respective average people per household on the slide before. Our second model was the carrying capacity model, a differential equation that links the growth of housing units, dn dt, to how close the current amount of housing is to M sub h and M itself. The closer n is to n sub h, the slower the growth. If n is small, growth is also limited. MATLAB was integral to this model. Built directly into the software is the function ode45, which solves non-stiff differential equations such as this one. With 2 lines of code, one setting up the differential equation and the other solving it, we can easily manipulate the code to solve for any t in any data set. This was incredibly important to save time in our modeling. We could also freely manipulate the k value to maximize the calculated Pearson correlation coefficient, a well-known measure of fit. This malleability also plays a significant role in our sensitivity analysis, which we will see after the results. Note here that the graphs are scaled down by 100,000 houses. Seattle experiences a large growth around 60,000 houses, tending towards 470,000, while Albuquerque has little growth, to only around 270,000, with only 10,000 new houses in 40 years. Our team then utilized sensitivity analysis to determine how stable and valid our model is in different conditions. We changed 2 factors, the maximum housing population and the growth constant k. New M sub h's were arbitrarily chosen above and below our calculated value. The alternative k values, on the other hand, were calculated using the compound annual growth rate of each city. Albuquerque had a low growth rate of 0.0069, while Seattle had a growth rate of 0.0175. These were both compared to an arbitrarily high rate of 0.09. The sensitivity analysis corroborated our expectations, showing the model's robustness. Similarly, the carrying capacity shifted. The final values shift to match the capacity. Similarly, changing the k value increases and decreases housing growth as expected. Changing the carrying capacity has a larger effect than changing k, implying that our precise calculations of M sub h play a pivotal role in our final model. Reflectively, we found both limitations and strengths with our model. First, with both models only being one equation, this simplicity allows our team to fully trust the model and the results. The models are intuitive as well, as they are built for populations and provide rational results that make sense, not only for the requested 50 years, but hundreds of years in the future if necessary. We can precisely predict changes in population in both the short and the long term. Finally, having multiple factors such as population, carrying capacity, and people per household allowed us to tailor our model to each specific city, not just a general fit. However, one factor that we ran out of time to investigate was the city's relationship between median income and housing supply. Realistically, as prices continue to rise faster than median income, fewer people can afford a house. Quantifying this would have likely strengthened our results.
Question 2 asks us to forecast the future homeless populations in Albuquerque and Seattle over the next 10, 20, and 50 years. For this problem, we had 3 assumptions and justifications. First, the population model in Part 1 appropriately predicts the housing populations for the next 50 years. Secondly, based on research, approximately 95% of homeless people will stay homeless the next year. And third, per capita homeless populations accurately reflect how non-homeless populations transition to becoming homeless due to the flexibility of the 2 states. Using these assumptions, we developed an asymmetric Markov chain model with 2 absorption states, where SH is the percentage of the homeless population that returns to being homeless, and CH is the percentage of the non-homeless population that becomes homeless. To achieve results, we first use our logistic model from question 1 to predict future values for the population of non-homeless individuals. With this data, we use the following recursive equation to derive our predictions of the homeless population, where HI is the population of homeless individuals at time I, and PI is the predicted population of non-homeless individuals. This model is preferable to polynomial regressions or exponential growth models because it considers the carrying capacity of the population and the movement of individuals between these 2 states. In addition, MATLAB's array features allowed for simple implementation of the Markov chain, where we iterate through the years and update the HI plus 1 values based on the HI and PI values. For our results, we found that Seattle's homeless population will increase to 31,000, 41,000, and 56,500 in 2034, 44, and 74 respectively. Albuquerque's will increase to 7,000, 9,500, and 12,500 among the same years. Graphically, we can see that this growth mirrors the carrying capacity growth we saw in question 1, which reaffirms the purpose behind using this model. To test the validity of our model, we altered the SH and CH values by 5% in both directions. In addition to seeing directly proportional shifts in the predicted homeless population, changing SH appeared to have a larger effect on the population, indicating a need to focus on year-over-year trends in homelessness. Overall, our model had strong adaptability with the ability to readily change the input data and model parameters. In addition, our model had cohesion with the Q1 model, given that it was used for Q2. However, due to the limited amount of states considered, our model can be considered oversimplified because people may not just exist between homeless or non-homeless states, as we're going to see in question 3. Finally, the volatility in the stay homeless population can be considered a weakness because results that best match reality would likely require extremely precise data.
Finally, Rising from the Abyss asks us to address long-term homelessness in our chosen city of Seattle. We were tasked with creating a long-term plan using modeling, factoring unforeseen circumstances. A key assumption for the second part of our solution is that rapid rehousing or transitional housing, also known as temporary housing for those looking for sustainable permanent housing, has participants that will leave at the end of the month after they find sustainable housing, and that the chance of finding sustainable housing each month will remain constant. We believe that this is a fair assumption because rapid rehousing allows for up to 3 months of residency, but it makes sense for individuals to leave if they no longer need the program. In addition, the randomness in housing availability means that there should not be significant month-to-month changes in availability, and this significantly simplifies the situation for being modeled. Since there are many solutions that have already been proposed and implemented, we decided that a multi-criteria decision model would be a great way to determine the best plan moving forward, factoring in factors such as cost, emotional benefit, the chance of preventing future homelessness, as well as wait time. This also accounts for the unexpected circumstances because they would affect the data for one of these criteria. The first part of our metric is gray relational analysis, which calculates weights for each criteria based on the non-beneficial and beneficial criteria, and also the significance of that final metric, to produce a metric between 0 and 1, with 1 being the ideal and 0 being the non-ideal. Additionally, both parts of our model, as will be shown, will solve the evaluation matrix with m rows and n columns based on the number of solutions and also the number of criteria. The second part of our model is TOPSIS, or Technique for Order of Preference by Similarity to Ideal Solution. So the best option will have the greatest Euclidean distance from the worst option and also have the smallest Euclidean distance from the ideal solution. The weights are determined using the entropy method, which measures the dispersion among the data. And as seen in the code, MATLAB was extremely useful during our competition window because it could quickly calculate matrix and list space operations quickly, which was crucial during the time limit. As seen in our flowchart for TOPSIS, after normalizing the matrix, the positive and negative ideals can then be determined, and then a performance score for each solution can be produced, with 1 being the ideal and 0 being the negative ideal. Additionally, to create our final metric, we decided to average both the metrics from gray relational analysis and TOPSIS to both combine their strengths and mitigate their individual weaknesses. For example, gray relational analysis is good with fuzzy data, which is especially useful with our data for emotional benefit. But it also assumes a linear relationship between the criteria and the alternatives. TOPSIS is good with outliers and also accommodates many alternatives, but it assumes independence in the data and also fixed weights. As seen in our model, we considered the main methods of permanent stable housing, Section 8 vouchers to reduce rent, as well as rapid rehousing, and as well as combinations of 2 methods. And as shown from our metric, rapid rehousing was deemed to be the most beneficial long-term plan. Now that it has been established that rapid rehousing is the best method moving forward, we can evaluate its current impact in Seattle by creating a queuing model. Starting with a 3-month success rate of 70%, that corresponds to 33% per month. And as in the queuing flowchart below, those who do not find sustainable housing after 3 months will be returned to the unhoused category. Here, the RAND function in MATLAB was extremely useful for generating a table of random numbers between 0 and 1, which allowed us to simulate the success for each participant and whether they ended up finding sustainable housing. This also allowed us to simulate the program over multiple months and years, which allowed us to produce more long-term results as well. As seen in the results, about 1,700 people with a standard deviation of 30 were able to find sustainable housing in 1 year, whereas about 8,400 with a standard deviation of 60 were able to in 5 years. To test the sensitivity of our model, we varied both the capacity, or the number of people who could use this program, as well as the 3-month success rate, each by 10%. And the results show that our model is fairly robust, with having no extreme changes from small changes in our input data, but also that it would be able to accommodate for these changes in our data and the adaptability. Some strengths of our methods were that we used multiple multi-criteria decision models and combined their strengths together by averaging them together, which allowed us to better represent the situation of the data. Additionally, we showed modeling depth because not only did we consider multiple important criteria from a range of different solutions, but we were also able to evaluate its impact using a decision model, or using a queuing model for the best known solution. Finally, because the weights were objectively determined in gray relational analysis and TOPSIS, we introduced minimal bias into our final metric. Some limitations were that with more time, we would have liked to consider more data and criteria, and that our metric values do not stay constant because they depend on the number of criteria, the number of solutions, and the data for each of those solutions. Finally, we assume perfect time transitions in our queuing model, such as instantaneous time transitions.
At the end of the 14 hours, we are very proud with the paper that we produced. We would like to thank our coach, Ms. Winkler, the Blake School, SciAm, Jane Street, and MathWorks for making this opportunity possible for all of us. Thank you for listening.
Great, thanks for the presentation. So maybe Kelly will start us off with a question.
Yeah, I have a question on your Markov chain. You said the SH state is absorbing, but you had the probability of staying in the state was 95%, is that correct?
Sorry, could you repeat the question?
That you have your Markov chain model, you had 2 states, one of them is the SH, and you state that the SH was an absorbing state, but the probability of staying in there was 95%, is that correct?
Yes, that's correct.
So what happens to the other 5%?
So the way that the asymmetric Markov chain works is that we use the logistic model from question 1 in order to fully flush out the population of non-homeless individuals. So the reason that we used a per capita amount of homeless people to estimate how people change from the non-homeless population to the homeless population is because that change accounts for or is reasonable to mirror the change that's going to be going back into the non-homeless population. So essentially it was a combination, or that logistic model in question 1 accounts for the change in, or the people that are essentially moving back into that original state.
So but then for your Markov chain then, again, I'm not sure I understand how the Markov chain then is then linked to the other model.
Yeah,
Those probabilities aren't balanced.
yeah, so here, I can go back to the original slide. So the idea of a asymmetric Markov chain is that the probabilities are not intended to be balanced in the first place because of the fact that when we had our logistic population model in the first question right here, we subtracted for 2010 to 2022 the homeless population data from the total population data, which gave us the population of basically non-homeless individuals, and then used this logistic population model to extend it all the way through 2074. So once we had that data, then we didn't necessarily need to be involved with how people were changing back to the non-homeless population, but instead simply how they were changing either from the homeless population back or from non-homeless to homeless.
Okay, but then in your code, in that for loop, you were just taking a percentage of the population of non-homeless and shuffling them over.
Yes,
Can you show the code?
yes.
Yeah, so the second branch, that's in yellow then. And how does that correspond then to the logistic model?
So the logistic model is simply to achieve the PI values all the way through 2074. So in this case, we haven't shown the stored data that we use to fit the PI model for the using MATLAB's curve fitter functions. But that data is essentially incorporated into this code in order to achieve like the HI+1 values for every year.
So then where is in your sixth line there, you set P, and then you're using P inside the loop.
Right, but the outcomes of P are not like of importance.
Right, but you're using the future P values inside that loop.
Right. Okay. I think it's possible that I understand your point, but I think it's possible that this might have been maybe a slight misrepresentation of the actual code that was used in the to solve the problem. But I can assure you that what we did was extend the P all the way down and not like recursively use P to update the HI values.
Okay, thank you.
Sand, you have a question?
Hi, everybody. Thanks for a nice presentation. Can I just give you one little bit of feedback on the sensitivity slide? I think it was maybe second to last slide. Right, I would have loved to have seen percentages rather than numbers. I think you, right, yeah, just to see how things change when you change the input variables by 10%, what the percentage change with the outputs, okay? Okay, so my question is, I think early on and maybe midway, you did different types of models. Like in the beginning, you did a logistic model, and then you did a differential equation, the carrying capacity model, maybe you use OD45 and all that sort of stuff with that. Can you comment on, I don't know, maybe the different results or what you felt with the outputs with regards to the different models, how they compared?
Yeah, so the main point of using the logistic model in the first place is that the logistic model only accounts for the data from 2010 to 2022, so only 12 years. And that's what we use to figure out the equilibrium point, the M sub P. But we chose the carrying capacity as our final model to represent our results because it's iterative. It uses the years before number of housing and in its function to calculate the next years. So that's why we used it, because it allows us to kind of take the data that we have and extrapolate it and use the data predicted to calculate the next years.
Okay, that's the logistic, right? And then,
The logistic was just the first part. The carrying capacity was the differential equation that allowed us to, it was reiterative. It allowed us to kind of move our data from being 12 years to all the way up.
and then later on, you did, you used a MATLAB curve fitter for various things versus another approach for sensitivity. And, you've tried different techniques to come for the same results, right? Can you comment on those and how those, your results compared, which one you preferred over the next? Anything?
Here, I can take that question. So one thing that we essentially kind of ran out of time to include in our paper was out of sample tests. So for when we're talking about why the carrying capacity model or why our multi-criteria decision-making model are preferable to other models like just an exponential model where we don't consider that there's a maximum limit to what Seattle and Albuquerque can house, that's based on the idea that when we conducted those out of sample tests, the difference between predicted values that we already had, such as in 2021 or 2022, were the most similar to their actual values themselves.
Yes, yes.
Go ahead.
It is about third part of the challenge. You have a nice graph about unhoused people transitioning to housed. Can you? Yes. So it is about third of unhoused population to transition to permanently housed every month. Like 1 month and third goes to permanently housed. But after 3 months, third goes back to unhoused, and 33% goes to permanently unhoused. What happens to the remaining 34% of people there?
Yeah, sorry. Oh, is this on? Okay. Yeah, sorry. What we meant to say with the ending 30% is 30% of the original number that entered the program would be returned to the unhoused. So our 70% success is saying that after the 3 months, 70% were able to find permanent housing, and then the remaining 30 would re-enter the unhoused population.
Okay.
Not that 30% of the month 3 participants.
Okay, okay, that makes sense. Yeah, thank you.
Okay, great. I think in the interest of time, we'll wrap it there, but thanks, guys.
Thank you.
Thank you.